Welcome to This Explainer. Today, we're popping the hood on artificial intelligence. We're going to cut right through all those media buzzwords to understand how these machines actually process information and make decisions. If you've ever wanted to truly unpack the building blocks of AI, you are in the exact right place.
Here is our roadmap for today. We'll start by defining AI, look at its foundations, understand AI agents, explore problem-solving through search, see how machines actually learn, and wrap up with a deep dive into decision trees. Let's jump in.
Section 1. Defining artificial intelligence. So the term artificial intelligence was actually coined by John McCarthy, and his vision for it was incredibly profound. He wasn't just interested in building a neat parlor trick that blindly mimics human behavior. No, the real goal was to build systems that could apply the fundamental principles of intelligence to literally any intellectual task.
And that brings up a really fascinating tension in AI design, one that's been there from the very beginning. When we build an AI, are we aiming for human fidelity or rationality? Look, if we choose fidelity, the goal is to perfectly mimic us, cognitive flaws, biases, and all. But if we aim for rationality, the system's only goal is to maximize a performance measure to achieve the absolute best possible outcome using whatever computational models gets it there.
Now, if we do lean toward human fidelity, we have to look at Alan Turing's famous 1950 test. To behave indistinguishably from a human, an AI needs a massive toolkit. We're talking natural language processing to communicate, knowledge representation to remember things, automated reasoning to draw conclusions, machine learning to adapt, computer vision to see, and robotics to physically interact with the world. It is quite the checklist.
All right, moving on to Section 2, the foundations of AI.
You know, it's easy to think AI is just a bunch of folks writing really complex code, but the foundation goes so much deeper than that. It is a highly interdisciplinary masterpiece. You need mathematics to compute probabilities, neuroscience to figure out artificial neurons, psychology to understand how human thought works, linguistics for language, and honestly, even economics to help agents make the most cost-effective decisions. The whole shebang is built on a multitude of scientific disciplines.
Okay, Section 3, Understanding AI Agents.
Now that we've got the philosophy and the foundations down, let's talk about the actual vessels of AI, the agents. In this world, an agent is simply anything that can perceive its environment and act upon it. Think of sensors as a machine's eyes and ears, collecting data from the world. And the actuators? Those are its hands and legs, the mechanisms it uses to actually change or interact with that world.
And this creates a brilliant, unbroken loop. The environment throws out percepts, which the agent takes in. Inside, a program processes all that data to make a decision, and then executes actions back onto the environment. Whether we're talking about a robotic vacuum navigating your living room or a digital assistant filtering out your spam emails, this loop is constantly running in the background.
But agents definitely evolve in complexity. We start at the baseline with simple reflex agents that just react, kind of like an automatic streetlight turning on at dusk. Then model-based agents step it up by keeping an internal memory of the world. Goal-based agents actually plan ahead to reach a destination, like your phone's GPS. Utility-based agents go a step further. They don't just want to reach the destination, they want the absolute most efficient, happiest route possible. And finally, at the pinnacle, learning agents can actually critique their own actions and get smarter through experience over time, a real game changer.
Which leads us to Section 4, problem solving through search. Once an agent is placed in an environment, it has to figure out how to navigate it, right? Generally, it uses one of two methods. An uninformed or blind search explores every single possible option systematically. It's basically like wandering in a pitch-dark maze, keeping your hand on the wall until you eventually stumble out. It works, but it's incredibly slow. An informed or heuristic search is totally different. It uses extra knowledge, a heuristic, to estimate the cost to reach the goal. It's like having a compass pointing right at your objective. Because it's guided, heuristic search is way more efficient and absolutely essential for complex AI apps.
So, Section 5, how machines actually learn. How exactly do we get from a machine that just searches a maze to one that actually learns from its environment? Well, machine learning rests on three massive pillars. First up is supervised learning, which is like using flashcards. We give the AI the questions and the correct answers, so it learns to predict future ones. Second is unsupervised learning, where we dump a mountain of unlabeled data and force the AI to uncover its own hidden patterns. And third is reinforcement learning, where the agent learns purely through trial and error, almost like training a dog with a system of rewards and penalties.
Let's bring this all together in Section 6, deep dive, decision trees.
To truly cement all these abstract concepts we've talked about, let's look at a highly concrete mathematical example of a supervised learning model, the decision tree. The mathematical goal here is incredibly elegant. It relies on two core concepts: entropy, which is essentially the measure of pure confusion or uncertainty in a dataset, and information gain, which is the reduction in that confusion after you ask a question. At every single branch in the tree, the AI calculates the exact question that removes the absolute most confusion. It's this elegant, high-speed mathematical game of guess who.
Imagine our AI agent is trying to decide whether to wait for a table at a restaurant. It looks at its sensors and asks its first question: are there patrons? If the place is completely full, it mathematically calculates the next best question to reduce confusion. What's the wait time? Or maybe, how hungry are we right now? It just keeps branching down, layer by layer, relentlessly slicing away uncertainty until it reaches a totally logical final action. Yes, wait, or no, let's leave. It is such a beautiful visualization of a machine making a strictly rational decision.
As you digest all the incredible mechanics we've explored in this explainer today, from the interdisciplinary roots all the way down to the entropy calculations of learning trees, I want to leave you with one big foundational question. As we continue to advance, what is our ultimate endgame with artificial intelligence? Are we, as a society, trying to build machines that perfectly mimic human thought, complete with all of our quirks, biases, and flaws? Or are we striving to build systems that achieve perfectly rational, mathematically optimal outcomes? The answer to that question is going to define the entire future of our relationship with technology. Thanks so much for joining me to explore the anatomy of AI today.